Видишь, он...
Да.
Good evening. We have a guest from the University of Loughborough tonight. This is Evgeny Ferapontov.
Прошу прощения, практически ничего не слышно.
А сейчас?
Очень-очень тихо.
У вас микрофон выключен?
Нет, должен быть. Олег, сейчас, подождите, сейчас попробуем разобраться.
Боря, а меня слышно?
Очень-очень-очень тихо, практически не слышно.
Давайте
Ну, у меня почему-то так. Виноват.
Ну, у меня нормально. У меня нормально.
Тогда это проблема что-то у вас, видимо. Okay, so the topic is Lagrangian multiforms and integrable dispersionless systems. Evgeny, you're welcome. Please.
Thank you very much. It's a great pleasure to be here in person. So the title is Lagrangian multiforms. I will define everything. Multiforms. I will abbreviate them as LM and dispersionless integrable systems. So this is a joint work with Mats Vermeeren, who is actually represents two schools who introduced Lagrangian multiforms: Berlin School of Zurich and Leeds School of Frank Nijhoff. And Mats was, he is now in Loughborough. He was a student of Yuri Zurich and then a postdoc in Leeds. So he knows both approaches to Lagrangian multiforms. And the plan is the following. So first of all, I will define Lagrangian multiforms. Then I will discuss Lagrangian multiforms and conservation laws, higher conservation laws of linearly degenerate PDEs, of PDEs in 3D, linearly degenerate PDEs in 3D. And finally, Lagrangian multiforms and Gibbons-Tsarev equations and Gibbons-Tsarev equations in 4D.
Riva al mare è difficile erano in casi molto particolari avere proprio una superficie completamente, può capitare, ma era però è uno stagno, quelle dal punto di vista della meccanica, le onde nel stagno della mare si assomigliano.
Raffaele? Let me start with Lagrangian multiforms. So let U be a function of x1, independent variables x1, xn. It could be a vector function, but I will assume that U is a scalar function. In all my examples, U will be just a function of n variables. And I will denote Ui is first order partial derivatives, Uij, second order partial derivatives, and so on, standard jet notation. So Lagrangian multiform. Lagrangian multiform is a differential form by the way, I'm not an expert in Lagrangian multiforms. The subject is new to me. But when I looked at the formulas people write in this field, I noticed some links to dispersionless integrable systems, to something I know. And in fact, in this talk, I will just show you some examples and observations. I have no theorems. We have no kind of rigorous proved results. We have observations which I think are of interest. Yeah, is a differential form of the following form. It's sum over I is less than j, Lij, dxi, dxj. I will be looking at two forms for definiteness. Okay, again, all my examples will be two forms, right? But it could be n form, not n form, k form, k less than n. So where Lij are functions of, for definiteness, let me assume that they're functions of xi, xj, u, uxi, ui, uj, and uij.
But only the same ij.
Yeah, same ij, same ij. Lij are functions of just these variables with the same indices, I and j. Yeah, it's not so important. You can include here partial derivatives with respect to other variables, and you can include all x's, all partial derivatives, all second order partial derivatives. Doesn't matter. But in this case, Euler-Lagrange equations will be relatively simple, right? In general case, they are more complicated. So multiform Euler-Lagrange equations. What are multiform Euler-Lagrange equations? Follow from the condition. So we introduce S gamma action integral over a surface, two-dimensional surface gamma of this differential form L. And we require that this that U is such that this action is critical for any gamma, for any surface gamma, right? So as gamma is critical for any surface, two-dimensional surface gamma, right? So let's assume, for instance, let's do an example. Let's take two-dimensional surface, which is just coordinate surface of xi, xj variables, right? So fix I and j, and we look at two-dimensional surface, coordinate surface. Then everything else disappears, and Lagrangian multiform is just this. It restricts, it's just this. And then we have to calculate the ordinary Euler-Lagrange equation, right? So if you require that this is critical, okay, for coordinate plane, then you have to calculate delta Lij by delta U equals 0. Standard Euler-Lagrange equation. So standard Euler-Lagrange equation has to be satisfied for every coordinate plane, right? But not only this, we can restrict, for instance, this to form on any other plane, on a skew plane, two-dimensional plane.
Normally, I mean, the traditional one which we know is when there's just a one form, right?
It's a two form on
Yeah,
a
but I'm
surface.
saying the one that we know, the standard thing from classical mechanics is a one form.
Yeah, one
right?
form.
And then
Yeah.
you are looking for a
Curve.
which is
Yeah.
the analog of your surface.
Yeah.
But then there is a special curve which is stationary for that. So this is not the same. You said that you're supposed
For
to be
all
stationary
curves.
No,
For
it's
all
not. It's
curves.
not for all curves.
No, but this is what Lagrangian multiform is about. It gives you Euler-Lagrange equations, this condition of extremality of this action gives you PDEs for this function U, all right? And so this restriction is extremal for any surface or any curve, depending on the type of the form.
Usually, if it's a curve, you'll find
Uh,
the curve is special. It's not true for all curves. Anyway, I'm burning time. Sorry.
Right, no, but this is the definition of Lagrangian multiform. You require criticality with respect to every surface. Of course, it's a very strong constraint, right? So, Euler-Lagrange equations are as follows. I'll write down Euler-Lagrange equations in the assumption that Lij depends only on xi, xj, ui, uj, uij, no other derivatives, right? Then we have the following set of Euler-Lagrange equations. Delta Lij by delta u is 0 for any ij. This you get when you restrict to a coordinate plane, right? Then you have to just, you get just this, no sum here, you get just this, and you take standard Euler-Lagrange equation, right? But then there are other relations. I'll write them down. dLij by duj minus di, oops. Не помню так хорошо. I think it's all right. Minus di dLij by duij. Duij plus dl this plus dl ik by duk. I will not be using these equations. I'll just write them to show you how they look in general, right? They're not so nice. Minus di dlik by uik, and this has to be 0 for any ijk. And the last one, dLij by duij plus dl jk by dujk plus dl ki by duki equals 0. Right, so these three sets of equations.
What is G?
Partial, just...
This total...
No, this is just...
No, GI in the middle formula, yes.
Here.
No. In front of
di
this.
d by dxi. D by dxi.
Just
Yeah, partial derivative by dxi, yeah. And here as well. So these are Lagrangian multiform equations. So in general, if you take this at random, write down these equations, they will be inconsistent, right? So we require that this system is an involution. So far as I know, there are only examples, many examples of Lagrangian multiforms where this system is an involution. There are no classification results. For instance, can we classify such functions Lij so that this system is an involution?
And this
right?
isn't some natural thing like some d by dl, some dl equals 0 or something.
Yeah, it's when you ask this thing to be critical for any surface, you get this, and this.
But it cannot be written in some compact like dl equals 0 or something. dl, where d is some.
I'm not aware of this.
You know,
I don't know.
It should be something like that. Some exterior derivative.
Let me write you equivalent form. these equations are equivalent to another set of equations. So let's calculate differential of L. Yeah, differential of this form. It's a 3 form. And so it's sum over ijk. So here I will write dxi, dxj, dxk, dxk. And here, this coefficient somehow it factorizes aijk times bijk, where these are certain differential polynomials in U and its derivatives. So we have this factorization. Yeah, just standard differential. Yeah, usual differential. Differential. I'm not sure about horizontal.
Because if you take standard differential,
By-
you will have DUI.
Exactly, that's what I was thinking. Yeah,
No,
that was my
like
question.
when I differentiate Lij by x,
Yes.
I use total derivative by x.
Yes.
Yeah.
Horizontal differential.
Horizontal differential. So, and it is observed that in many interesting examples, this DL factorizes in this form. I'll give you an example in a second. And it turns out that this set of equations is equivalent to the following. Aijk equals 0 and Bijk equals 0. So, so in the terminology of Lagrangian multiform people, they say that L has a double, differential of L has double zero. So because both of these must be 0. So in other words, these equations are equivalent to these equations. And this is easy to kind of memorize. You don't need to memorize these complicated equations. You just take differential, it factorizes, and then you write these equations. These are Lagrangian multiform equations. Now the most interesting, meaningful example. Let me discuss this example. So Lij is the following. Lij equals Uij squared. Sorry. Ci minus Cj Uij squared divided by Uiuj. So let's take this one.
This is the only term, yes? Or
Yeah, Lij is this expression. No explicit dependence on x's, no explicit dependence on u, only on first and second derivatives, right? Let's take this expression. So now it's direct check that if you calculate DL, yeah, differential of this, you'll get this factorization where Aijk is this, Aijk. I'll write it explicitly and you will recognize something familiar. Ci minus Cj Uij divided by Uiuj plus Cj minus Ck Uik Uiuk plus Ck minus Ci Uik Uiuk. And by the way,
So that
if
must
you
be JK then. Must be JK here in that case.
Ujk, yes, thank you, Ujk. So, and if you set this equal to 0, because we have to set this equal to 0, you'll see it will be Veronese web equation, right? Veronese web equation, because you multiply, clear the denominator, and it will be Uij times Uk, and so on, right? So you get equations Aijk equals 0 is Veronese web hierarchy, right? Now, what is Bijk? Bijk also something familiar. Bijk equals the following. Uijk, third order derivative, minus 1/2 Uij, Uik over Ui plus Uij, Uij, Ujk over Uj plus Uik, Ujk over Uk. Right. So let me erase. So and by the way, okay, I'll make this comment later. So now, what is Aijk equals 0 is Veronese web hierarchy. And Bijk equals 0 is also a well-known system, especially for Sergei Tsarev. Right? It means that the following metric, let's take the metric of the form Ui dxi squared. So it's Yegorov potential metric. Yeah. So let's take this potential metric, and then it turns out that this condition is equivalent, that this metric has diagonal curvature. In other words, all these curvature components are equal to 0. In other words, it's a semi-Hamiltonian metric, right? So what is interesting here? First of all, the system Aijk equals 0 and Bijk equal to 0. First of all, these equations separately are integrable and involutive. They're compatible, right? They form 2 plus 1 dimensional Veronese web hierarchy. These equations separately are integrable and compatible in involution, right? And they characterize Yegorov metrics with diagonal curvature.
You mean involutive if you take different indices? Or
Yeah, so all
different
consistency,
curvatures of the 3 indices?
all consistency conditions are satisfied here, right? What is amazing that if you add these two equations together, then these equations are in involution, right? All together. So this system together is involutive, right? But it's no longer, this is 2 plus 1 dimensional, this is 2 plus 1 dimensional. When you add them together, it becomes 1 plus 1 system. But well, I still can't understand why equations coming from completely different contexts. Veronese web hierarchy describes GL2R structures, so it comes from one geometry. Yegorov metrics come from hydrodynamic type systems, another geometry. Why are they compatible? In other words, what is special about those GL2R structures described by these equations that satisfy additional constraint Bijk equals 0, and the other way around? What is special about Yegorov metrics which satisfy Veronese web hierarchy? Right? I don't know a good answer to this. All right. What is another interesting phenomenon that occurs here? So let's write down this equation: delta Lij by delta U equals 0. It's one of the raised Euler-Lagrange equations, multiform Euler-Lagrange equations. When you restrict this form to coordinate plane, then it becomes standard Lagrangian. You calculate its standard Euler-Lagrange equation. It will be this. Let me write this equation down explicitly. It will be this. I'll write it down explicitly. Uij squared over Ui Uj ij, it will be fourth order PD. Fourth order PD, sorry, it's I, index I, plus uij squared over uiuj, ui squared, uj, ui, uj squared, j, plus 2uij over uiuj, uj, ij equals 0, right? It's a fourth order, you see, because of this term, it's a fourth order PD in just two variables, right? And it's quite, I think it's not at all obvious that this equation follows from these two, right? Because each of these equations involves three variables, ijk, right? This involves ijk, this involves ijk, but this involves only two variables, I and j. Somehow, if you play with these equations, you can get this one, which is quite a non-trivial calculation. It's not immediately obvious, right? That you can get this equation. And by the way, this equation is known in the literature. It's called the sigma model equation. It governs harmonic maps into a space of constant curvature. I don't want to stop on this, right? So it's another geometry which appears in this context. Why are they kind of compatible? All these geometries compatible? I don't know. I don't have a good explanation for this.
You mean this two-dimensionless reduction of something three-dimensional or not?
No, this two-dimensional is a corollary of this. It's not a reduction. It's a corollary. It follows from these two equations, right? From both, not from one, from both. Yeah. So and this is not obvious. All right. It's quite a long calculation to derive this from these two, right? All right. So one remark. So what does it mean that dl equals 0? Remember, dl equals aijk times bijk. We have this factorization, dxi, dxj, dxk. Dxk. Right, so let me write this relation in the following form. dl equals 0 mod aijk equals 0. Right. Then this means that L is a conservation law of the Veronese web hierarchy, right? Because aijk are these equations. These things equal 0 is a Veronese web hierarchy. So in other words, L is a second order. It's a second order conservation law. You see, it has uij squared here. Is a conservation law of the Veronese web hierarchy. Right. So let me now, and it's a general kind of principle, I think, that all Lagrangian multiforms can be viewed as conservation laws of linearly degenerate PDEs in 3 dimensions. So
in the case when coefficients factorize of coefficients of the differential.
Yes, but it's always the case somehow.
It's always the case.
Yeah. There are no theorems, rigorous theorems. What you can prove, if there is a factorization of this kind, then Euler-Lagrange equations that I erased here follow from this equals 0 and this equals 0. But other way around, there is no result. But in all examples, they're just equivalent. This equals 0 is equivalent to the Euler-Lagrange equations. Right. So what I will do next, I'll just show you a few more examples of this kind. I'll take a familiar equation. It's called Mikhailov equation. It's one of the linearly degenerate PDEs in 3D. There is a classification of such PDEs. There are 6 of them. One is Bereneza-Webb equation. There are 5 more. And one of them is Mikhailov equation. Let me write it in this form. U33 minus U12 plus U3 U11 minus U1 U13 equals 0, right? And let me call this left-hand side, I'll call it M for Mikhailov, right? N equals 3 now, yeah, now N equals 3. Ij equal 1, 2, 3, right? So, first of all, I think at least this fact was new to me. This equation possesses what was known, it possesses first-order conservation laws, and 4 of them, actually. 4 first-order conservation laws. What was new to me, that it possesses 3 second-order conservation laws, right? In fact, I believe it possesses higher conservation laws as well, right? Local, yeah? 4? Right. Right. So it's is it a kind of, is it published somewhere? Oh, that's good. You'll give me a reference. Yeah. So let's take. So what I will do now, I will calculate a few second-order conservation laws of this PD. No, it's not Lagrangian. No, it's not Lagrangian. By the way, the idea of Lagrangian multiforms was to kind of put integrable hierarchies into Lagrangian framework, right? For instance, we have this Veronese-Webb hierarchy, and the idea was to kind of write a Lagrangian of this kind, which produces equations of the Veronese-Webb hierarchy. Unfortunately, it doesn't work like that, because Euler-Lagrange equations for this Lagrangian produce not just equations of the Veronese-Webb hierarchy, but also these equations, Bijk equals 0, which form a constraint, a differential constraint. Still, there is no Lagrangian multiform that would produce these equations alone. At least I'm not aware of such multiform. Okay, so I will be looking at conservation laws of this equation, f dx2 dx3 plus g dx3 dx1 plus h dx1 dx2. Then its differential dl, you can easily calculate. That's f1 plus g2 plus h3 dx1 dx2 dx3. And we will see that this expression for conservation laws of this equation. So I'll take second order conservation laws. I'll show you FGH later, right? So this expression factorizes. One factor will be Mikhailov equation, right? It's a conservation law, so it has to be 0 by Mikhailov equation. So my Mikhailov equation will be a factor times something else. So this will be my Aijk, and this will be Bijk, right? So Ijk are 1, 2, 3, so I don't use indices here, right? So it's Mikhailov equation times another differential expression. And let me show you what comes out for different conservation laws of the Mikhailov equation. So we'll be getting this kind of factorization in all examples, and the system m equals 0 and sigma equals 0 will always be compatible. So second order conservation laws produce Lagrangian multiforms. Yeah? In involution. Meyer bracket vanishes. So formulas are a bit messy, but let me show you one of them, at least. Because these conservation laws are not so elementary. So let's take the following.
No, we understand your question that you asked.
Yeah. That's why. You see, in all examples that we have, M is, okay, the equation sigma is characteristic of the conservation law, right? And in all examples, M equals 0 plus sigma equals 0 is a compatible system for some reason, right? In all examples that we have, just automatically. Let me show you. 2 U3 U11 minus U12 U13. I'm writing one of the components of the conservation law. Minus U1 U3 U11 squared plus 2 U1 U11 minus U13 times the Mikhailov equation. Right? Strictly speaking, Mikhailov equation is 0. I don't need to write it here, right? But if I write it here, the factorization will be much simpler, right? So I need it here to make the factorization more natural, right?
Everything is multiplied by a.
No, just the last bracket. The last bracket, yeah, as written. Yeah, as written. M is this. F is this F, yeah? I'm writing you components of the conservation law. The rest will be easier. And H, U1 squared, U11 squared, minus 2 U1, U11, U13, minus U3, U11 squared, and plus U11, U12, plus U13 squared. So I claim that this is a conservation law, high conservation law of the Mikhailov equation. So Oleg, you're saying that there are, so we found 3 of them. We found 3 of them.
There are 4 more.
But higher order. Third order. Or which order?
Sigma is called cosymmetry.
Okay, yeah, cosymmetry.
The Mikhailov equation has 7 conservation laws with cosymmetries of the third order.
Okay. No, then there is no contradiction because I know this has 4 first order conservation laws.
No.
Plus 3 second order conservation laws. This makes it 7. What do you mean? What do you mean? There are this equation has exactly 4 first order conservation laws that depend only on U1, U2, U3, not on second order derivatives. There are 4 of them. This I know, right? And we found 3 conservation laws of second order of this kind. I'm writing you the simplest, in a sense.
And there are 4 more. Perhaps the 4th order, but the cosymmetries are of the 3rd order.
Cosymmetries are of the 3rd order. No, cosymmetry will be of the 3rd order here. Yeah.
And you will write 3 cosymmetries of the 3rd order.
Yeah, that's right.
There are 4 other.
Maybe we will return to this later. Yeah. So for this conservation law, we have F1 plus G2 plus H3 equals twice Mikhailov equation times this sigma. I'm writing sigma U1, U111 minus U113 plus half U11 squared, right? By the way, to get this exactly this expression, I need this m here, right? If I don't use m, I will get something more messy, right? And this is if you set u1 equals v, u1 equals v, then you get v1 minus v13 plus half v1 squared equals 0. This constraint, right? This is called Hunter-Saxton equation, right? It's a known PD, right? And remarkably, it's compatible with Mikhailov equation, Wien involution, right?
You just denote.
This is what I called sigma, sigma, right? And there is one more example. So we did calculations for all three conservation laws, for all 3 second-order conservation laws. In the first case, you get MKdV as this sigma. In the second case, you get Hunter-Saxton, and in the third case, we get so-called Gurevich-Zibin system. Gurevich-Zibin system. Yeah, I can write it down. Yeah. So so this is, let this be case one. Case one. And this will be case two. Let me not write conservation laws. F is complicated. G is simple. G I can write. U1, U11 minus U13 all squared. They're quadratic, by the way, all these high conservation laws are quadratic in second-order derivatives, right? Quadratic in second-order derivatives. And H is, okay, another few lines. Let me not write them down. So only G is simple. Let me write down factorization. F1 plus G2 plus H3 equals minus 2m times the following. Okay, let me write it explicitly. Times the following bracket. U1 squared plus U1 squared U111 minus 2U1 U113 minus U11 U13 plus U133, right? And this expression, so when we equate it to 0, right? When we set this equal to 0 and we call V equals U1, then this equation can be written in the following form. D3 minus U, actually, we don't need. D3 minus U1, D1 squared applied to U1 equals 0. This is the equation, right? This equation is this. You can group them, simplify. So you see, you apply D1 squared to U1, so you get third order equation, right? And Gurevich-Zibin system is the thing where you put here n. It's integrable for any n. In fact, linearizable. Appears in general relativity somehow. It describes something in general relativity. I'm not prepared to speak about this. All right. So here, what appears here is n equals 2. All right. I thought, but what Oleg is saying contradicts what I thought. I thought that for any n, there is a conservation law which would produce this. But Oleg says there are only finitely many of them, so probably n equals 2 is specific. But in any case, I don't have results for other values of n. I only have for n equals 2, right? This is a linearizable equation. Maxim Pavlov studied it. He showed that this Gurevich-Zybin system equation is linearizable by reciprocal transformation. All right. So you can play this game with any linearly degenerate PD, integrable PD in 3D, right?
And if you have a Pavlov equation plus a higher flow of the hierarchy, can you put them to the same Lagrangian?
Yeah, but wait, it's again the same happens. There will be an extra constraint. You can't put them like Veronese web hierarchy, all right?
Connected with the hierarchy.
Yeah, but if you take Veronese web hierarchy alone without any additional constraints, I can't represent it using with a Lagrangian multiform. I get constraints as well. Yeah, so this Lagrangian multiform that I wrote at the beginning, it produces Veronese web hierarchy with a constraint.
So you'll start from Lagrangian multiform with, say, 4 variables if you have one more time, yeah?
Possibly, but this hasn't been done. All right. So you can construct many more examples of this Lagrangian multiforms. If you take, say, even for Mikhailov equation, as I said, it has 4 first-order conservation laws, which depend on U1, U2, U3, first-order derivatives, right? And 3 second-order conservation laws. You can take the linear combination, right? It will be quite a long expression. You can play the same game. You'll get factorization of the same kind, Mikhailov equation, times some quite a long expression, but they are compatible for some reason, yeah? And that's why I asked Iosif whether it's a general phenomenon that if you take say a higher conservation law of a PD, then it has a characteristic, and then you add this characteristic as a differential constraint. So you consider your PD, and you also set characteristic equal to 0. Is it always an involution? At least it is in all these examples.
It's called symmetry reduction.
Is it really? But
you take the so-called Lagrangian extension of your equation and take a symmetry of this Lagrangian extension. Symmetry is compatible with equation, and the solutions are called invariant solutions.
no, symmetry, yes, but this is cosymmetry. Is it still?
But since your equation is Lagrangian,
It isn't. It isn't. With a constraint. Yeah, it's okay. 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 So yeah, and another set of examples where Lagrangian multiforms naturally appear are Gibbons-Tsarev equations. So let me just show you one example. Second heavenly equation. I will erase this. All right, so second heavenly. I'll just go through the main steps, try not to write too many formulas. So it's this equation. Theta, U will now be theta. Theta Tx plus theta Zy plus theta Xx, theta Yy minus theta Xy squared equals 0. So second heavenly equation. Why is it important? Because if we write the corresponding metric, G equals dx dt plus dy dz plus, yeah, it's a Monge-Ampere equation. It's called symplectic Monge-Ampere equation, right? Theta yy dx squared minus 2 theta xy dx dy plus theta xx dy squared. So let's write this metric. Then this metric is self-dual and Ricci flat. And theorem of Plebanski says that every self-dual Ricci flat metric can be written in this form where theta satisfies this equation. So this equation governs all self-dual locally, all self-dual Ricci flat metrics. Huh? Signature 2-2, yeah, signature 2-2. Yeah, that's right, yes. Neutral signature. So to apply a method of hydrodynamic reductions to this equation of this kind, I need to write it in quasi-linear form first. So let me briefly sketch this. So set, let me introduce variables theta xx equals u, theta xy equals v, theta yy equals w, theta xt equals p. And then from this equation, I will have theta zy is expressed in terms of v, u, w, and p. Okay, so I introduce 4 variables, u, v, w, p. And then now I will write down all possible compatibility conditions between this. Yeah, so for instance, this differentiated by y equals this differentiated by x, and so on, right? So then let me write this quasi-linear system. Uy equals vx, ut equals px, vy equals wx, vt equals py, vz equals v squared minus vuw minus px, and the last one, wz equals v squared minus uw minus py, right? So this is an equivalent form of this strongly nonlinear equation. This is quasi-linear system. And now what we do, we look for a solution for solutions of this system in the form u is a function of n Riemann invariants, Rn, and so on. V is a function of n Riemann invariants. W and P is a function of the same Riemann invariants. And about Riemann invariants, we assume the following, that they satisfy the following equations. RIT equals lambda I RIX, RI equals mu I RIX, and RIZ equals eta I RIX. Right? So this is my ansatz. I'm looking for solutions to this system in this form where u, v, w, p are functions of n Riemann invariants, and these Riemann invariants, they satisfy a triple of commuting hydrodynamic type systems. Right? It's a general method of hydrodynamic reductions. And then when you plug this, U, V, W, P into the system and differentiate using chain rule, you'll get differential equations for these functions, lambdas, mu's, etas, and these functions U, V, W, P, and they're called Gibbons-Tsarev equations, right? In general, right? Gibbons-Tsarev type equations, because Gibbons and Tsarev did it for dispersionless KP equation. All right, then I will not write all of them, but if you play with these equations, then they can be reduced to the following pair of simple equations. Mu ij, mu's are these characteristic speeds. Mu ij, j's derivative equals mu j minus mu I all squared divided by cj minus ci uj, and uij equals twice mu j minus mu I cj minus ci uj. Yeah, you get this. And also all other, so u is this u, right? This u. So for u and mu, you get these equations. And other variables can be expressed in terms of this u and mu. I'm not writing all formulas, right? This is what you get at the end. These are the key equations. Now, where here ci are either constants or in general arbitrary functions of Ri. Yeah, either ci is a constant or without any loss of generality, you can say ci equals just Ri. So in other words, ci equals constant or ci equals Ri. All right. So it turns out that if we eliminate mu's from this system and write this system in terms of u only, right? So how can we do this? Let's look at this, for instance. At the last equation, what does it? I can write it as follows: Cj minus Ci Uij Ui Uj equals to mu j minus mu I. Yeah, I get this. It's equivalent form of this one. And then I take the sum of three terms, mu j minus mu I minus mu k minus mu j. I get Veronese-Webb equation from here, all right? And if I differentiate this by index k, uijk, if I calculate uijk, I get this Yegorov condition, which I wrote at the beginning. So in other words, this Gibbons-Tsarev system for second heavenly is precisely the system I started with, all right? And we did some calculations, analogous calculations for other heavenly type equations. We get something very similar, right? So we always get Gibbons-Tsarev equations come from a Lagrangian multiform equations, right?
Have you tried to do a similar calculation for the general heavenly?
You see, I tried for the first. For the general, I haven't. But since all of them are equivalent, I'm not expecting anything, substantially different.
The general would be
More symmetric, maybe, yeah, maybe. On the other hand, I don't know. No, we haven't tried. So you see, it looks like Gibbons-Tsarev equations in 4D is another source of Lagrangian multiforms. But these are examples. We have no general theorems, general results, right? So I think I'll just stop here.
Okay.
Yeah.
Interesting. Thanks a lot.
Mhm.
Questions, remarks? Okay.
Uh-huh.
Женя, thank you very much again.
Uh-huh.
And it's nice to see you here. in
Thank
flesh.
you. Thank you. Yeah.
Yeah. So we meet in a week, and the next talk will be by Rafael Nicola.
Mhm.
Goodbye. Mhm. Загадочно.
Да, как-то все загадочно.
Мгм.